Hi, this is your video for section 11.3 about the inference about two means with independent samples. The objectives in this section are first to test hypotheses regarding the difference of two independent means, and second to construct and interpret confidence intervals regarding the difference of two independent means. So first we're going to look at how to test hypotheses. So in this section we discuss methods for using sample data from two independent samples to test hypotheses made about two population means, or to construct confidence interval estimates of the difference between two population means. So the difference in this section is that we're talking about independent samples, where in the last section we talked about dependent samples. So for our hypothesis testing, we'll use sample data from two independent samples to test a claim made regarding two population means. Since we have two independent samples and two different population means, then our population parameter is the difference of those two means. So it's mu1 minus mu2. The requirements to do this type of hypothesis test are first that the sample data are independent. Both the samples have to be simple random samples. And for both of the populations that we're looking at, they either have to be normally distributed or the sample sizes have to be large, which means both of them have to be at least 30. The last one is that for each sample, the sample size can be no more than 5% of the population size. The notation in this section, since we're dealing with two independent samples and two means, we just have subscripts for everything. So for population 1, our mu sub 1 is our population mean, n sub 1 is the size of the sample, x sub 1 bar is the sample mean, s sub 1 is the sample standard deviation. And for population 2, we have all the same symbols, only with subscripts of 2 instead of 1. Our test statistic is given by this formula. On the top, we're subtracting the two sample means. On the bottom, we have the two sample standard deviations. For each one, we're squaring it and then dividing it by the sample size for that sample. Just remember, if you're doing this by hand, to use order of operations. So you would square here first, then divide by the sample size, do the same thing here, then add, and then take the square root. One of the hard things in this chapter is figuring out when you have the case of independent samples and when you have the case of dependent samples. So two samples are independent if the sample values selected from one population are not related to or paired or matched with the sample values from the other population. The samples are dependent if the sample values are paired somehow. So each pair of sample values either consists of two measurements from the same subject, like before and after data, or each pair of sample values consists of matched pairs, such as husband and wife, mother and daughter, etc., where the matching is based on some relationship. So let's look at the different steps of our hypothesis test. These are the same steps that we've talked about before, just we're going to look specifically at how it works for independent samples and testing means. So our step 1 is still to determine our null and alternative hypothesis, and we want to start by writing down the claim or the statement. This one's a little bit different because when we go to translate this into an alternative hypothesis, we actually have two parameters. We have the mu1 and the mu2 that represent the two population means. We're still looking at using an inequality, so we have to figure out whether it's going to be a less than, a greater than, or not equal to. And here's where it gets just a little bit different. When we go to write down our alternative hypothesis, we're going to write it down one way, and then we're going to use algebra a little bit to change what it looks like. So first we're going to write the inequality with the mu1 on the left side and the mu2 on the right side. So we'll either have mu sub 1 is greater than mu sub 2, mu sub 1 is less than mu sub 2, or mu sub 1 is not equal to mu sub 2. The reason that we're doing that is because it's really easier to think about just how the two means are going to compare. Once we get that done, then the way we want to have it written in the end is with both of our means on the same side. So to do that, we'll subtract mu sub 2 from both sides. That way we'll have mu sub 1 minus mu sub 2 on the left side and 0 on the other side. We'll still have the same inequality symbol that we used up here. Once we get the alternative hypothesis written, then we'll do the null hypothesis just by replacing the inequality with an equal sign. So here's an example of writing the hypotheses. A researcher wants to know whether state quarters have a weight that is more than traditional quarters. He randomly selects 18 state quarters and 16 traditional quarters and weighs each of them. So first we're going to write the claim. The claim is that the average weight of state quarters is more than the average weight of traditional quarters. Our first question is, how can we tell whether this involves dependent samples, matched pairs, or independent samples? So if you look at the problem, there's no mention of pairs, and the most important thing in this one is that the sample sizes are different. If you have two different sample sizes, then there's no way it can be matched pairs. So this has to be two independent samples. So now we're going to translate our claim into an alternative hypothesis. Our two populations are state quarters, population 1, and traditional quarters, population 2. And that's just because that's how they're mentioned in the problem, that they mention the state quarters first and the traditional quarters second. We're going to use mu sub 1 and mu sub 2 to represent our population means. So what inequality should we use? The claim says that mu sub 1 is more than mu sub 2, so this translates to a greater than. So first we would write our alternative hypothesis as mu sub 1 is greater than mu sub 2, and then we would subtract the mu sub 2 from both sides to get mu sub 1 minus mu sub 2 is greater than 0. So our alternative hypothesis is mu sub 1 minus mu sub 2 is greater than 0. Our null hypothesis is that mu sub 1 minus mu sub 2 is equal to 0. Here's another example. Many studies have been conducted to test the effects of marijuana use on mental abilities. In one such study, groups of light and heavy users of marijuana were tested for memory recall. Test the claim that the population of heavy marijuana users has a lower mean score than the population of light users. So first write the claim as a complete sentence. The mean score on memory recall tests for heavy marijuana users is lower than the mean score for light marijuana users. Again, how can we tell whether this involves dependent samples or independent samples? Again, there's no mention of pairs in the problem. It just talks about comparing the two means. So in this problem, there's no before and after. There's no mention that that the two samples are related to each other in any way whatsoever. So to translate the claim into an alternative hypothesis, we could say the two populations are heavy marijuana users, population 1, and light marijuana users, population 2. And again, that's just because they mentioned heavy marijuana users first in the problem, and we mentioned them first in the claim. What inequality should we use? The claim says that mu sub 1 is lower than mu sub 2, so this translates to a less than. So we would write our alternative hypothesis first as mu sub 1 is less than mu sub 2, and then rewrite it as mu sub 1 minus mu sub 2 is less than 0. So here's our alternative hypothesis, mu sub 1 minus mu sub 2 is less than 0, and our null hypothesis is that mu sub 1 minus mu sub 2 is equal to 0. Okay, now let's go through a whole hypothesis test. So we have some data here that represents calories per serving in 2 random samples of hot dogs. These tests were conducted separately for beef hot dogs and meat hot dogs, which are a combination of pork, beef, and poultry. We're going to test the claim that the average number of calories in beef hot dogs is different than the average number of calories in meat hot dogs, using the 0.10 level of significance. So step 1, our claim is that the average number of calories in beef hot dogs is different than the average number of calories in meat hot dogs. Since beef hot dogs are mentioned first in the claim, we'll define those as population 1 and meat hot dogs as population 2. How would we know that these are independent samples? There's no mention of paired values. It just says there are 2 random samples that were selected. And the 2 averages are mentioned separately. So our parameter is the difference of the means, mu sub 1 minus mu sub 2. What inequalities should we use? The claim just says that the averages are different. It doesn't say anything about less than or more than, so this is just going to translate to a not equal to. We would first write our alternative hypothesis as mu sub 1 is not equal to mu sub 2, and then subtract the mu sub 2 from each side to get mu sub 1 minus mu sub 2 is not equal to 0. Here's our alternative hypothesis, mu sub 1 minus mu sub 2 is not equal to 0. Our null hypothesis is that mu sub 1 minus mu sub 2 is equal to 0. For step 2, a type 1 error would be supporting the claim that the average number of calories in beef hot dogs is different than in meat hot dogs when the 2 averages are actually the same. The significance level in this problem was given as alpha equals 0.10. For step 3, here's our formula for our test statistic. So we need the sample statistics, the mean, the standard deviation, and the sample size from each sample. We had the original data, so we could use our calculators or StatCrunch to come up with our sample statistics. And remember, we're looking at each one separately. So here we have our sample mean, standard deviation, and sample size for the first sample from the beef. And here we have our sample mean, standard deviation, and sample size from our second sample, which was the meat hot dogs. So we're going to plug all those numbers into the formula. So we're just putting all the numbers from sample 1 on the left of this formula and all the numbers from sample 2 on the right. So if we work that out, we're going to get a test statistic of 1.393. Step 4, since our alternative hypothesis had a not equal to, that means this is a two-tailed test. And we're using the t-distribution. So here's our picture. We have t equals 0 in the middle. Our test statistic was 1.393, so it goes over on the right side of 0. Because this is a two-tailed test, we're just taking whichever side of 0 the test statistic is on and using that tail. So we're going to find the area to the right of our test statistic. And here for our degrees of freedom, we use either n sub 1 minus 1 or n sub 2 minus 1, whichever one is smaller. In this problem, they're both the same. 17. So we'll use 17 degrees of freedom. So to get the area to the right of our test statistic, we do TCDF from 1.393 to 1000 with 17 degrees of freedom and get 0.0907. Since this is a two-tailed test, we have to multiply this area by 2, so that gives us 0.1814, and that's our p-value. Now we're going to compare the p-value to alpha, so we have 0.1814 is less than or equal to 0.10, which is false. That gives us negative conclusions, so we would say do not reject the null hypothesis. And for step 5, we want to write our final conclusion. Again, this is negative, so we say there's not sufficient evidence to support the claim that the average number of calories in beef hot dogs is different than the average number of calories in meat hot dogs. if we're going to use technology for this, we can use StatCrunch. If we had all of the data in StatCrunch, then we'd be doing t-stats to sample with data. And in this, you want to uncheck the box that says pool variances. So we're doing a hypothesis test. Our number on the other side of our null hypothesis was 0. Our inequality was a not equal to. And here would be our hypothesis test results. Notice they got the same test statistic that we did. Their p-value came out a little bit different because they use a formula to calculate the degrees of freedom. We're using a much simpler version to get the degrees of freedom, but our result is more conservative, so our p-value came out a little bit bigger than theirs did. Objective 2 is to construct and interpret confidence intervals regarding the difference of two independent means. So for a confidence interval estimate of mu sub 1 minus mu sub 2, that's our parameter that goes in the middle of our confidence interval. Our lower limit is going to be our point estimate, which is the difference between the two sample means, minus our margin of error. Our upper limit is going to be our point estimate plus our margin of error. And here's the formula for our margin of error. Again, we're using the t-distribution for this to get our critical value. And the rest of the formula looks very much like what we just did in our hypothesis test to get our test statistic. It's part of that formula. And again, for our degrees of freedom, we're using the smaller of the two sample sizes, -1. So let's look at an example of constructing a confidence interval for the difference of two means. So we're going to use the same sample data that we used in the hot dog example, and we're going to use that to construct a 90% confidence interval estimate of the difference between the average number of calories in beef hot dogs and the average number of calories in meat hot dogs. So here were our sample statistics. Now what we're trying to estimate is the difference between the mean number of calories in beef hot dogs and the mean number of calories in meat hot dogs. So our point estimate is just the difference between our two sample means. So it's the 167.8 minus the 157.4, and that gives us 10.4. So this is estimating how much difference there is between the average calories in the two types of hot dogs. We're estimating here that there's about 10.4 calories difference. Now what we're trying to get is a 90% confidence interval. So for a 90% level of confidence with 17 degrees of freedom, and in this we're using the t-distribution, so we would do inverse t on our calculator. We have 0.05 because again we find the alpha, which would be 10% or 0.10, and divide it by 2. Our degrees of freedom is 17. That gives us a critical value of 1.74. And again, on your calculator, this will come out to be a negative number, and you just take off the negative. Then our margin of error is going to be our critical value, 1.74, times this value, and this is just, again, plugging our standard deviations and our sample sizes into the formula that we saw on the last slide. So once we do all that, we get a margin of error of 13.0. So to get our confidence interval, we're taking our point estimate, which was the difference between our two sample means. So we're taking that 10.4 plus or minus our margin of error, which was 13. So if we subtract the 13, we get a negative 2.6. If we add the 13, we get 23.4. Now the interpretation of this is that we're 90% confident that the difference between the average number of calories in beef hot dogs and the average number of calories in meat hot dogs is between a negative 2.6 and a 23.4. Now here, because we're looking at the difference between our two population means, the difference can either be negative, which would mean that the average for the beef hot dogs is actually less than that for the meat hot dogs, or it can be positive, which would mean that the average for the beef hot dogs is greater. Because we've got one of each, we've got one negative value and one positive value in our confidence interval. That means that 0 is included in this interval. That means that our true difference between the two population means could actually be 0, which would mean that the two population means are actually the same. So this implies that there's not a significant difference between the two averages. In other words, the difference between the averages could be anything from negative 2.6 calories, implying that the beef hot dogs have fewer calories, to 23.4 calories, implying that the beef hot dogs have more calories. So this isn't giving us an answer as to which one actually has more and which one actually has less.